Share screen. Share. Okay, so let's see what happens now. Yes, fantastic. Right. Okay, so in Tut6 6.1, this is now just the normal Tut6 6.1. You are given two pieces of information over here. So you are given the ideal conversion that you expect based on published data where you know this researcher did lab work free of external diffusion. Now you build your reactor and boo-hoo, you didn't do a great job because your real conversion is 80%. And you've excluded any other effects like pressure drop maybe, but this is a liquid phase reaction in any case. So pressure drop will not affect the rate because of the incompressible nature of my system. So you had the real conversion and you were asked a few questions. You had to find that Kc value. This is a first order reaction, so we could go through the videos, make sure that you understand why we could apply this effective rate constant, only because it's first order. So when we equate out to rate equations, mass transfer rate to the intrinsic rate, replace CIS with CI bulk, we get an effective rate constant. The reason why I write this in terms of the Ki double dash, the area-based one, is in question B of this TUT. I changed the particle diameter. So if I change the particle diameter, what is important to know is that my volumetric rate constant that I can calculate, because I have Q and I have Ca naught, and I can in fact calculate that this is just my mole balance over there, analytical solution of my mole balance for a first order reaction. I can solve Ki, the volumetric rate constant. But Ki is equal to Ki double dash, the area based one, times AC. And AC is equal to 6 over rho C times divided by the particle diameter. And in part B, I change dP. So I must just remember, so if you get part B wrong in Tut6 6.1, just the normal one, the unchanged one, just remember that your Ki will change. Your Kc will also change because of the proportionality with the dP value according to the Teunis-Kramer equation. So Kc is going to change, AC is going to change, and if you want to use an volumetric effective rate constant, Kc will change, AC will change. And remember, it's often the most frequently made mistake in part B is that people use the Ki, the volumetric rate constant calculated over here for that rate, without realizing that this is actually Ki double dash times AC. Right. Okay. So now this is what we've done for Tut6 6.1. We could calculate our volumetric rate constant from our ideal conversion. What is the true rate constant? I could calculate AC, all the information given to calculate AC, and I could get my Ki double dash. Right. And using the real, just repeat that analysis. Very easy, because I can now find an effective K from my mole balance. Okay, because I know, let me just maybe large eraser. Because in my mole balance, I can now apply that effective K value with my concentration. So I know that my dFA dV is equal to min Ki double dash A. No, sorry, no. We've now got an effective rate constant, sorry. So here we've got min Ki effective that I am going to measure. And if I measure the area-based one, I need to remember that I've got an AC that I need to apply, Ci bulk, or you can calculate like I have done over here, just the volumetric one. So min Ki effective times Ci bulk, which is Fa over Q, and then I can separate my variables, write this in terms of X and integrate. So this is just the equation that I write. You don't even need to write it in terms of X. You can just keep it in terms of Fa in this case, because Fa naught was given. So you can integrate and you can find that effective rate constant when your real conversion is 80%. And then from the relationship, I like using this form if I have first order reactions because it's easier for me to solve the rate constants there. And I know Kc is a double dash kind of rate parameter, and I've got Ki double dash, which stays constant, and I could solve Kc. And now, if I change the diameter, I could change my K values and get the new conversion in my reactor. Okay, but they're just setting the scene. But now the question arose, how will I solve this if I do not have a first order reaction? If I do not have a first order reaction, so I kept my inlet variables the same, and I just pretended in that 6.1 that I have second order reaction. So everything else stays the same. I've given the ideal and I've given the real one, and I've got my AC. So of course my mole balance now changes. You can go and inspect maybe whether this is correct. So if I have a second order reaction, just to remind you once again, what I'm doing there is dFi is equal to min, and this is my volumetric rate, Fa squared divided by Q squared. And then I can just dFa over Fa squared from Fa naught to Fa is equal to min Ki V over Q squared. Right, so it's quite easy to then do this analytically and solve my Ki. I can also, if I want to use my skills or refresh my skills, what I've done here, so I've solved that Ki. I divided by AC because I realized that this is actually Ki double dash times AC. Right, and regardless of the units, this thing just translates whatever the units of this thing. So it's going to have a more complicated unit set than just the first order one. There's no dash there. No. Let me just do. So this is the volumetric rate constant that I'm busy calculating. This is just that I can use it with first order, second order. Its shape look exactly the same, that conversion factor. So now I calculated my Ki value. Right, and just to show you here, maybe I could just test whether my numerical integration, how good my solved IVP actually works in order to, with my analytically solved rate constant, where was it? Here. So I used just a function, the PFR reactor, and now I've got my Ci bulk. I have Ci bulk is equal to Ci surface for the ideal case. Ci surface. So if I integrate over my volume range, starting at my initial conditions, my conversion, let me just run all to make sure that it runs. Okay, there later on is errors because I still need to build my code for this to solve for Kc. So now I am asked to, for the real scenario, solve for Kc. And now I cannot just use an effective K here. So I can't use an effective K with Ci bulk here. That's illegal. That is like you are excluded from the rest of the test. Okay, so please do not do that. What we have to use, large eraser, where is it now? Sorry. Come on. Yeah, I've got it. So what we have to use in order to solve this, and this is actually the equation, just remind yourselves, this is the equation we use to solve AC, no, Ci bulk minus Ci surface is equal to, and now I have a Ki, the volumetric rate constant, Ci surface squared. Right, so this is what I now have to solve in order to get Ci surface, right? And I now know this Ki. I solved this from the rate where I know that this Ci surface was equal to Ci bulk. So this is known in my equation. This is known. My bulk concentration is going to change, but I know it at the inlet. My AC value is known, but I have to solve for Kc. So if I now want to modify my rate equation over here, what I must realize is this must now be Ci surface. So if I want to integrate and I want to calculate the concentration, it can't be Ci bulk. So I still send Fa as my dependent variable to this function, but I have a Ci surface that I have to solve for. Right, so now I am going to build a little solver into my code over here. So I'm just going to have a define solve CAS. There is that I'm going to solve there, and I have one equation. Equation 1 is equal to KC times KC times CA bulk minus CA surface. Okay, and my second equation is equal to KI times CIS squared. Have I typed it correctly now? Yes. And just return 1 minus 2. And then you've solved it. Okay, so my CIS that I am going to use is equal to F solve. And I want to solve CIS. And I have to give it a first guess that I know it's going to find the correct root. I know that it must be between 0 and CA bulk, so I'm just going to use CA bulk, not there, but divided by 2. So now solve. What's the problem in that part of the code? It needs a KC. KC is the one I need to solve for. So let me just do the following, because I eventually want to put this into a solver. But where do you start guessing for KC to make sure that your X-solve converges? So let me just first not apply it in a solver function. Let me just guess values for KC, and I'm going to use my KI double D just as a guide to say, all right, what is it equal to? KI double D, right? Let's just hope this runs, and I'm going to test then. So let me just quickly go through my code. What I'm calculating here is I integrate, and I just get my last value for FA out of that volume of my reactor, and I calculate the conversion. Right, so all of you should be familiar with that. So let's just see if it runs. Oh, my word, that didn't make any difference. Can you see there? So there, so let's just see if I multiply by 0, 1. Okay, and shift enter. Okay, that's going in the right direction, but it's still not small enough. So let me see if I make it really small. Okay. That's too small, so at least I know. So I can now keep on doing this. Ta-da, ta-da, repeat, 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 until this value converges to my final answer that I want. Or I can say, let me just build a little solver in here. So let's just solve for KC. And if I now solve for KC, I now just need to get my indents right. Check. Whoops. And right. So solve KC. So everything I want to now, I need a return function. So I need to write something that's going to go to 0 when this x is actually equal to my x real. So I am just going to return from that function that pink return x test minus x real. Okay, so let's see if this is going to work for me. So I want to solve my KC. It is going to be solve, please, my, what did I call it, solve KC. And now I need to supply a guess value, but at least now, and you will see if you use this very non-linear nature of these equations that you have to solve, especially later if we have to employ, temperature effects, becomes really hectic to find this first guess. So it's actually a very good idea just to play around to see in which range should I make my first guess. So let's just give it 0.001 times KI and I double dash. No? Okay, so let's see if it runs. No pink screens, please. Let's go. Oh, so it's not making good progress. Let's just see, iteration is not making good progress. So, okay, either I made a typing error. Let's just see, check. Okay. So that one might have been too small. So let's just see what my case is that it solved. Okay, yeah, now look on. Can you see? And shift enter. Okay, so I solved this KC value. based on this, using my function over here. I'm not sure, maybe you can go through my code, and because I now code, het ek ietsie verkeerd gedoen? Did I do something wrong? Speak.
I think, I'm not sure, but in the second line, just below def solve Casey, should you not remove that Casey, because that then defines it over again? So then it can't iterate.
Where did I do that?
At the top in the second line.
Ach, my word. That's why it's not working. I should have removed that. Thank you very much. Okay, now just go back to my... Okay, no, that's why it's not working. Let's just check. Thank you very much, Philip. Did you see why he complained about my is my indents right now? So indenter, yeah, if indent, unindent. Okay, so now I'm sorry. Happier. Okay, let's see if it's happy now. I don't want to waste your time with my silly mistakes. CA bulk, expected unindent. Okay, now I have to do, okay, let me check all the comments. I can't read your comments now. Just can somebody tell me where I missed my indents? Where I messed up my indents now? Okay, sorry, I can't hear.
The CIB below PFR should be indented, and I think that
yeah. There we go. Return there. No, yes. Thank you. Is it better? Please run now. So you see, that's why you don't code for an audience. Okay, now my guess is way off again. Let's try it. Think. Oh, that looks better. So this was the value, this was initially, and that's why my previous one, I actually practiced this actually before I tried to code it on here, and I know that this is the correct value. So I just made that mistake of leaving that in there. So you see, I got sympathy with you guys who told me that I make silly mistakes in my code. So now I have solved my KC value, and I can now change, everything now stays the same as in my previous part of my code I can calculate a new AC value, and I can now calculate a new KC value, right? And now I want to solve there, I just want to, this part. So I just want to solve now for my new reactor there, and I'm going to have to do my indents back. Control Tink. There we go. And let me now just make sure that I now have my new value. So this is the new value, and this should be KI double dash times AC new. Okay, AC new, K double dash times AC new. AC, did I calculate? Yes, like, sorry, I'm using two different keyboards. This one is on numlock. AC new and AC new. I've calculated the new one there. We're almost done. New. And then the KC, AC, Just remember now I changed my AC. So everything, hopefully, new. There we go. Let's see if it works. Oh, there it is. New. Okay, there are better ways of doing this than what I'm showing you. Right, so checking. Let's see. Yes, what did I forget?
At the two equation in the solve CAS, you just need a multiplication instead of the underscore between KI double dash and AC new.
Thank you so much. I would have picked that up because it would have complained bitterly at me. Okay, so yes, like it's good to code in collaboration. Yay! Okay, so now I can calculate my new X new from everything there. X test. So let's just copy that there, and I think you get the idea. So this is going to be my X new that I'm going to.
How do you indent?
How do I do that in
How do you
batch?
unindent all of them at once?
I just use the, what's this, block hockey, shift and the square hockey. I will let me write something, shift and I don't know what it's called in English. So I just select everything. So I select everything, select, and then just use this on your keyboard, jink, jink, for backwards indent, and use this one for forwards indent. So it's the square bracket that my husband sitting next to me. He's helping me with my English. Okay, right. Does it make sense, Philip? Do you understand my words? Hello?
Yes, yes.
Okay. Thank you. Okay, right. So let's now check our X now. And yay, it worked. Okay, so I can see that I improved my conversion by changing this particle diameter. Yes, and I'm just in time for a few questions. Let me just go back, stop sharing the screen. Where is my collaborate now? And stop the recording. Oh, well, but just before we stop the recording, are there any other questions for the sake of the students who couldn't participate? Nothing. Going. Stop.